arm, that is fourth arm, is the combination of parallel combination of a resistor R2 and C2. This total network consisting of 4 arms is the Wien bridge network, which is used for feeding back in the oscillator circuit. You can look at and see here that output is taken within this point, which is nothing but the across the parallel combination of R2 and C2, and this parallel combination actually is a low pass filter, if you can visualize it, and the R1C1 parallel series combination acts as a high pass filter. In this circuit, at high frequencies, the reactance of this C1 C2 will be much less. We know that if frequency is high, Xc equals to 1 upon twice pi Fc. If frequency is very high, this may be closer to 0. Okay, that's what is said here. The reactance of the capacitor C1 C2 will be much less due to the which PO taken here. Once this is shorted or zero reactance, this node and this node is shorted by this C2 because its reactance is very less to that to 0, to that to 0. So the voltage DO will become 0 across R2 because it will be shorted by C2. Next, at low frequencies, the reactance of the C1 C2 will become very high. Okay, once it is very high, this will behave like a open. Okay, the output voltage once again will be almost 0 because if it is open, the input will not pass into the side, output side. Is it understood? Harsh Tripathi are there? Is there Harsh Tripathi? Then Pratham, Aman, Bushra?
Yes, sir. Yes, sir.
Understood. So this is understood or not? It's very simple things. You have studied the network theory, etc. Have you studied network theory in electrical department?
Yes, sir.
So these are all now funny for you. Understand very well. Between these two high and low frequencies, there exists a particular frequency at which the value of resistance and the capacitive reactance may become equal to each other, producing a maximum output voltage Vout here. This frequency is referred to as resonant frequency. And the resonant frequency for the Wien bridge oscillator is calculated as FR equals to 1 upon square root of twice pi square root of R1 C1 R2 C2. For R1 R2 equals to R and C1 C2 equals to C, we can write this frequency, resonant frequency, as 1 upon twice pi RC. Yes or no? Can we write it for this assumed value?
Yes, sir.
Okay. Further, at this frequency, the phase shift between the input and the output will become 0, and the magnitude of the output voltage will become equal to 1/3 of the input value. In addition, it is seen that the Wien bridge will be balanced at this particular frequency. Balanced means what is this balancing? Balancing is what?
Sir, the amplitude will be constant.
Based What? Tell.
Sir, in oscillation, the amplitude will be constant at the time.
Okay. Now balancing of the network is what?
Sir, potential at both the nodes will be same.
Both the node will be same. I mean resistance of one this way. If you take, then if you connect a galvanometer, it will be showing what? Other network also you have, I think,
Zero difference.
Yes. Tell.
No current will pass through them.
Yes. So anyway, this is known to you. Pitstone bridge, etc. You have studied. I think you will be aware of this. So in the case of Owen bridge oscillator, the Owen bridge network of figure will be used in feedback path. And see the connection of this feedback path. It is taken all the way from here through a coupling capacitor here and here. These are the three coupling capacitors, and two BJTs are used. And as the network gives no phase shift, this one bridge doesn't give any phase shift, so you need two BJT, 180 degree here, another 180 degree here. So altogether 360 degree. So phase shift should be what? 360 degree. Here it is a zero phase shift is offering, zero phase shift. So if you use only one, then your purpose is not being solved. We know that. We have discussed in the last class that there is a need of positive feedback and there is no phase shift or zero phase shift or 360 degree phase shift. Isn't it? We have discussed. Can you remember?
Yes, sir.
So two BJTs are required. This BJT connection is what kind of connection it is? Is which configuration it is?
Common emitter.
Common emitter. C stage. Okay. In these oscillators, the amplifier section will comprise of two amplifier formed by transistor Q1, Q2, wherein the output Q2 backfed as an input to Q1 through this network. So this network to this. The blue enclosure and the figure is the network. Well, this is talking about this one. Here the noise inherent in this circuit, obviously any circuit will have certain noise because of the capacitive coupling or because of the voltage fluctuation, temperature fluctuation, or etc. So that fluctuation or say noise will cause a change in the base current of Q1, which will appear at its collector, this point, after being amplified with a phase shift of 180 degree. Here it is going to be 180 degree phase shift. Okay, here it is 0 degree by the feedback network when bridge, but this amplifier Q1 is going to make 180 degree. Then another is there which will make another 180 degree. This is fed as an input to Q2 via C4. C4 is your coupling capacitor. Why coupling capacitor is used by the by?
For AC analysis.
Can we not connect like this directly?
So we can means there are three ways we can connect it: by transformer coupling and capacitor coupling and direct.
So why this coupling capacitor, if at all required? Why? Can we avoid it? If we don't do that, what may be the problem? What possibly may be the problem if we connect directly? DC couple, direct couple.
So if you connect it directly, then DC current will also pass, and
DC
that
current will also pass. Okay.
and then that may cause a amplitude swing.
See, come on. See, if you see this is for what? Tell me.
It's the voltage divider bias.
It is a voltage divisor bias. Okay. You need a particular voltage value here. Okay. That voltage value is created by this voltage divider, right? Maybe here you need, say, 0.8 volt. I am assuming roughly without any particular logic. Okay. We know that, of course, VB should be greater than 0.7 volt, then only it will be, there will be some, it will be forward biased or some current will flow. Assume that. So this needs 0.8 volt at least, greater than equals to 0.7 volt. Okay. Now point is, suppose this voltage value up here is maybe what? May depend on this and current flowing through this. Yes or no? So voltage developed here, VC Q1, for example, I'm taking. This voltage value may or may not be same. Okay, means if you connect directly like this, the VCQ1 will be affecting the bias of Q2, biasing voltage, that is base voltage, base emitter voltage will be affected. Sometimes it is not acceptable. So if you connect this coupling capacitor C4, then this DC bias is not going to spoil the, DC value at the collector of Q1 is not going to affect the bias, base bias or base emitter bias of Q2. Is it understood?
Yes, sir.
We have discussed
Yes, sir.
earlier also, but you have forgotten. We have discussed a little bit. Anyway, let us go ahead. So this is fed as an input to Q2 via C4 and gets further amplified and appears with an additional phase shift of 180 degree. As I said, 180 degree, another phase shift will occur. This makes the net phase difference of the signal fed back to the wind bridge to be 360 degree. Altogether, now it is 360 degree phase shift, which is required actually, satisfying the phase shift criteria to obtain the sustained oscillation. We know that this is going to be give a zero phase shift, this network, and we need 360 degree or zero, so we have to use to BJT. However, this condition will be satisfied only in the case of resonant frequency, due to which the Wien bridge oscillators will be highly selective in terms of frequency, leading to a frequency stabilized design. Only if it is at operating at resonant frequency, then only possibly the phase shift of 0 degree will be also obtained. Wind bridge oscillators can even be designed using op amps. Here is the example of op amp. The call is coming. Let me take the call. So here is the example of wind bridge oscillator using op amp. See how it is connected. This point is connected with the negative terminal, and this is with the positive of the op amp. It is to be noted that here the op-amp is required to act as a non-inverting amplifier, and that's why this way it is connected. Because if it is inverting, then there'll be a problem. Double op-amp may be required. So it can be used, op-amp, inverting and non-inverting both can be used. If it is non-inverting, then what is the gain of this amplifier? Have you used op-amp? Have you used earlier in your course?
Yes, sir. It was
Yes, sir.
1 plus RF by R.
Okay, good. So we'll be dealing with op-amp a little more in future. This is the application of op-amp in oscillator. Okay, we'll be talking in the fourth module. This is third module. We are going to finish it very soon. Maybe another lecture will be required for this. We'll go for the op-amp based many circuits. During that time, basic characteristics of op-amp will be discussed. Then further its application, various applications will be discussing. Okay, so during that time we'll see what are the gain, etc. If it is non-inverting, if it is an inverting, etc. we'll be discussing. For now, let us go ahead and finish this module. Okay, op-amp is required to act as non-inverting amplifier. As the Wayne bridge network offers zero phase shift, further the circuit is it is evident that the output voltage is fed back to the inverting and non-inverting both terminals here. It's talking about this both the term, inverting terminal and non-inverting terminal. Okay. Hold on. Let me take the call. Hello. Hello. এখন কথা বলতে পারছি না, ক্লাস চলছে, পরে কথা বল, ফোন করব। At resonant frequency, the voltage is applied to the inverting and non-inverting terminals will be equal and in phase with each other. However, even here the voltage gain of the amplifier needs to be greater than 3 to start the oscillations and equal to 3 to sustain them. In general, this kind of op-amp based Wayne bridge oscillators cannot operate above 1 megahertz. That's the limitation of this Wayne bridge oscillator. Its frequency range is very less due to the limitation imposed by the open loop gain, etc. Wayne bridge networks are low frequency oscillators and it can be operated in the audio frequency range, that is 20 Hz to 20 kilohertz. The oscillation frequency in this kind of circuit can be varied quite easily by changing the values of C1 and C2 capacitors. However, these oscillators require large number of components. As you can see here, you have the 6 components. So it is not that popular compared to other oscillators which we'll discuss very soon. That is crystal oscillator. The circuit diagram shown here is given in your book. So whatever we are discussing, same thing. This is nothing but the same Wayne bridge network. Is it understandable? Just orientation has been changed. Instead of placing in this area, it is kept here, and see the connection is always between this inverting and non-inverting terminal. Connection is from there. Is it understandable? If you want, you can see here. Same thing connected little differently, otherwise actually same. Yes, Pratham, is it understood? Same network. Well, when
Yes,
this
sir.
network has been connected and shown this in this book, textbook. Okay, and analysis also more or less same only, nothing more or less. An oscillator circuit in which balance bridge is used as the feedback network is the Owen bridge oscillator shown here. The active element is an operational amplifier, which could be VJT also, we have seen. And we'll discuss this thing in module 4 about the op amp, which has a very large positive voltage gain. I mean, this op amp is having what kind of characteristic that is said here. The characteristic of op amp is that its gain is very high, ideally infinite, negligible output resistance, RO. If I say RO, it is also infinite. Okay, and input resistance, sorry, zero. Output resistance is zero. Input resistance is infinite. Okay, very negligible means very low value of output resistance, very high or infinite value of input resistance. These are the very fundamental characteristic of other things like gain bandwidth product, CMRR, PSRR, etc. are there, slew rate. Those things will be discussing later in the fourth module. We assume further that AV is constant over the range of frequencies of operation of the circuit. Gain of this amplifier is constant over a wide frequency range. To find the loop gain minus beta A, we break the point here. We break the loop at the point marked P and apply an external voltage VO prime. VO prime is applied at this point P with respect to ground. Okay. See, this point is ground. It is not shown. You are not able to see it. Yeah. It is grounded. So VO, external voltage VO prime is applied at this point P with respect to ground between terminal 3 and 4 of this network, as you can see. Since VO equals to AVVI, VI is what? VI is the difference between this point voltage and this point voltage. That is, this voltage of this point is V1 with respect to ground. Voltage of this point 2 is V2 with respect to ground. So difference between this is the VI. As given here, VI equals to V2 minus V1, and we can write the loop gain of this as VO by VO prime. VO by VO prime. Which can be written as VI AV, because VO is VI AV, and VO divided by VO prime equals to minus beta A. Is it understood?
Yes, sir.
The loop gain is kept here for easy understanding from this equation. 70A equals to AV, that is gain, voltage gain, and beta minus beta equals to VI by VO prime. Beta of any network is, feedback network is what? Its output divided by its input. Input is given between these 2 points. That is VO prime. Output is the difference between these 2 voltage, that is V1 minus V2, that is equals to VI. V1 minus V2 equals to VI. So this part is input. So beta normally defined as what? It's output voltage, that is VI here, V1 minus V2 with the minus sign, and what is that? Input applied between these 2, 3 and 4 is your VO prime. That's what is said here. And now if you split it, this thing, okay, if you split it in this way, say V2 by VO prime minus B1 by VO prime, then you can write this thing. Can we do it or not? Pay attention. See, V2 is what? V2 is what? You have applied VO prime, and VO prime is applied here with respect to this point. So it is a voltage divider. See, is it not a voltage divider? And if you take this arm, what will be the voltage here? V2. V2 is equal to Z2. I can write VO prime into Z2 divided by Z1 plus Z2 or not?
Yes, sir. Z1 plus Z2.
Yes, sir.
Similarly, V1 good morning, sir. I am taking a lecture here, so I'll be calling later on. So V1 can be written similarly. If you think of this part, V1 is what? Again, VO prime into R2 divided by R1 plus R2, isn't it? Yes, Pratham?
Yes, sir.
Think this one. So it's a simple voltage divider. So it is not difficult to show that Z1 and Z2 have the same phase angle, and hence at a frequency of this it will occur. FO equals 1 upon pi RC. And at this frequency, Z1 equals to 1 minus J into R, and Z2 equals to 1 minus J into R by 2. Hence, V2 can be obtained as 1 by 3 VO prime at omega equals to omega 0. If a null is desired, null means V1 minus V2 equals to 0. Then R1 and R2 must be chosen so that Vi equals to 0. And from equation this equation, R2 by R1 plus R2 equals to 1/3, or R1 equals to 2R2. With this value R1 of R2, this is possible. Now, in the present case, where the bridge is used as the feedback network for an oscillator, the loop gain of equation this, that is what? Minus beta A, which we have seen here also. In the present case, where the bridge is used as a feedback network for an oscillator, the loop gain of equation this must equal unity and must have zero phase. Thus, since AB is a positive number, the phase of minus beta from equation 14-71 must be 0. Okay, but magnitude must not be 0. This accomplished by taking the ratio R2 by R1 plus R2 smaller than 1/3. Writing in different way, we can write, we have already seen this, V1 by U prime, this one, I mean to say this one we are talking about, or you can say this part we are talking about. So V1 by U prime equals to R2 by equals to 1/3 minus 1 upon delta, where delta is smaller greater than is a number greater than 3. If this is greater than 3, then only it is possible, and hence minus beta can be written as this. at omega was to 0, omega equals to omega 0, V2 by V prime is 1/3 and beta equals to minus 1 upon delta, and the condition minus beta equals to 1 is now satisfied by making delta equals to AB. So is it understood?
Yes,
Yes.
sir.
Note that the frequency of oscillation is precisely the null frequency of the balanced bridge given by equation 172. At any other frequency, V2 is not in phase with VO prime, and therefore Vi equals to V1 minus V2 is not in phase with VO prime, so that the condition minus beta A equals to 1 is satisfied only at the FO. FO equals to 1 upon pi RC. Now we'll start crystal oscillator. I mean, two oscillators are mentioned in your syllabus. One is what we have discussed, Wien bridge oscillator, and then another one is crystal oscillator. And Wien bridge oscillator is having a limitation of its frequency response. That is, its frequency of oscillation is within the audio range. What is that audio range?
20 hertz to 20 kilohertz.
20 to 20 kilohertz. Okay. So if you want for higher frequency oscillator, then you have to use crystal. What is that we'll be studying now. Quartz is a hard crystalline mineral composed of silicon and oxygen atoms. It is the crystalline form of SiO2, silicon dioxide. Basically an insulator. When a voltage source is applied to a small thin piece of quartz crystal, it begins to change shape, producing a characteristic known as piezoelectric effect. You all are aware of that. Yes or no? This piezoelectric effect is the property of a crystal by which an electrical charge produces a mechanical force by changing shape of the crystal and vice versa. Okay, just opposite is also possible. Okay, mechanical force applied to the crystal produces an electrical charge. This is what the characteristic of a quartz crystal. The quartz crystal used in a crystal oscillator is very small, thin piece of cut quartz with the two parallel surfaces. This is one surface, another surface is metallized. To make the required contact, you have to make a contact here. So you have metallized and a contact is given so that you can connect to a other circuit terminal. Okay. The crystal size and thickness of this piece of quartz affects the fundamental frequency of oscillations. It is also called characteristic frequency. Once cut and shaped, the crystal cannot be used at any other frequency than its fundamental frequency. In other words, its size and shape determines the fundamental oscillation frequency. If you cut it differently, its frequency, fundamental frequency will differ. The characteristic frequency is inversely proportional to its physical thickness. Thickness is more, frequency is less. A crystal can be represented by an equivalent electrical circuit, which is shown here. Equivalent electrical circuit can be used. It is a physical item. Okay, it's quartz, which its properties such that it can be characterized with L, C, and R, connected in series, and CP in parallel. So a crystal can be represented by an equivalent electrical circuit consisting of low resistance R large inductance L. LS is large. Okay? RS is small, and capacitance is a small capacitance CH. The equivalent impedance of the crystal as a series resonance uh, where CH resonates with inductance LS at a crystal's operating frequency. This frequency is called the crystal series. It is a series frequency FS. As well as this series frequency, there is a second frequency called parallel resonant frequency, which is resonates when LS and CS resonates with parallel capacitor CP. I mean, here you have this also in parallel. So this LS CS resonates with CP, then another frequency, parallel frequency is obtained. Parallel resonant frequency is obtained. And you see that the series resonance occurs at this frequency. This is a frequency axis, and their impedance is minimum, and that is equal to RS. And another frequency, the parallel resonance frequency, is AP, where maximum impedance occurs. Here, less than, when the frequency is less than the series resonant frequency, then the quartz behaves like a capacitive only. Then higher than that frequency, resonance frequency, it behaves as a inductive, and after again FP, it becomes capacitive. After the parallel resonant frequency behaves like. Now, these equations very known to you. R equals to Rn, XLS equals to twice pi FLS, XCS equals to 1 upon twice pi FS, FCS, and XCP equals to 1 upon. These are all known to you or not? These are fundamental equations related to R, L, and C. Yes? RLC
Yes,
circuit. At a particular frequency, the interaction between the series capacitance CS and the inductance LS creates a series resonance circuit, reducing the crystal's impedance to a minimum and equal to RS. I mean, this point is talking about. Here the impedance is minimum. This frequency point is called the series resonant frequency FS. And below FS, crystal behaves like a capacitive only. As the frequency increases above this series resonant frequency point, the crystal behaves like another, like a inductor. This point, or from here to here, okay, it acts as an inductive mostly. And it reaches a value of frequency just called parallel resonant frequency. At this frequency, the point, the interaction between the series inductor LS and parallel capacitor CP creates a resonant LC tank circuit. LC tank circuit, such as impedance across the crystal reaches the maximum value. Here, see that inductance value is maximum here. Maybe ZP you can call. Okay, here it is RS impedance. Here it is ZP at parallel resonant frequency. You can see that quartz crystal is a combination of series and parallel tuned resonant circuit oscillating at two different frequencies with very small difference between the two frequencies after cutting the crystal. Also, since the crystal can operate at either its series or parallel resonant frequencies, a crystal oscillator circuit needs to be tuned to one. Both cannot be used. I mean to say, It cannot be operated at series resonant frequency as well as parallel resonant frequency. You have to tune in such a way that it is operating at only one frequency. Okay. Series resonant frequency is given by this equation Fs equals to 1 upon twice pi square root of Ls Cs, and parallel resonant frequency is given by this Fp equals to 1 upon twice pi square root of Ls within parentheses Cpcs by Cp plus Cs. Some values are given here for finding out the series and parallel frequency values. So Rs is given as 6.4 ohm, Cs is given as 0.0997 picofarad, and Ls is given as 2.546 millihenry. If the capacitance across its terminal Cp is measured to be 28.68 picofarad, calculate the Fs and Fp. Putting the given values in the given equation, which we saw in the last slide, we can find out the values of Fs and Fp. Yes or no? We can find out easily.
Yes, sir.
You can see that the difference between Fs and the crystal's fundamental frequency, Fp parallel frequency, and Fs series resonant frequency. So this between these two resonant frequency parallel and series, there is not much difference, and the difference is about 18 kilohertz. 10.005 megahertz minus 9.987 megahertz. That's the difference between these two. However, in this frequency range, the Q factor, quality factor, you might have heard this Q factor. Yes or
Yes.
no?
Yes, sir.
Okay. Q factor of the crystal is extremely high because the inductance of the crystal is much higher. Okay, and Q factor is defined as XL by R. It is too high. Okay. And the Q factor of this crystal at series resonant frequency is given by twice pi FL by R, which is about 25,000. Q factor is 25, is quite high. The Q factor of 25,000 is because of this ratio XL by R. This high Q factor value also contributes to a greater frequency stability of this kind of oscillator. Typical crystal oscillators can range in the oscillation frequency from 40 kilohertz to more than 100 megahertz, depending upon their circuit configuration amplifying device. If this device is properly mounted, deformations like take place within the crystal and an electromechanical system is formed which will vibrate when properly excited. That is the behavior of the crystal. The resonant frequency and the Q depend upon the crystal dimensions, how the surfaces are oriented with respect to its axis, and how the device is mounted. So based on this, the Q factor also will be varying. The frequency is ranging from few kilohertz to few megahertz, hundreds of megahertz, rather 100 megahertz we have seen. And Qs in the range from several to 5, we have seen how much? 25,000 are commercially available. Okay. These extraordinary high values of Q and the fact that the characteristics of the quartz are extremely stable with respect to time and temperature account for the exceptional frequency stability of this crystal oscillator. I mean, it is a very good quality oscillator can be made with crystal rather than Wien-Gauge oscillator or Hartley oscillator or any other kind of oscillator. The few things which is given in your book is coming here now. Major things we have studied, understood, the fundamental things. Now few things about your book. So let us see what is given. So some typical values are mentioned here of the various parameters of this equivalent circuit of the crystal. The inductor L, capacitor C, resistor R are the analogous of the mass, the compliance or the reciprocal of the spring constant, and the viscous damping factor of the mechanical system. The typical values for a 90 kilohertz crystal are L equals to 130 nanohenry, C equals to 0.025, 0.0235 picofarad, and R equals to 15 kilo ohm, corresponds to a Q factor of 5500. The dimensions such as a crystal, such a crystal of such a crystal are 30 by 4 by 1.5 mm. It is these values of L, C, and R is specific to the dimension. Remember that. An example is given that if this is the dimension, possibly the values of L, C, and R are these, and corresponding to that, you will get a Q of 5500. And since C prime represents the electrostatic capacitance between the electrodes with the crystal as the dielectric material, as if from here to here you have the crystal as a dielectric material, then what is the capacitance between these 2 points? That is what your C prime. Okay, and it is quite larger than C here, which is only 0.0235 picofarad compared to C prime as almost equals to 3.5 picofarad. Quite large or not? C prime and C is a lot of difference in the values. If we neglect the resistance R, the impedance of the crystal is a reactance X, Jx, whose dependence upon the frequency is given by this equation, minus J by omega C prime into omega square minus omega S square divided by omega square minus omega P square, where omega is given as square root of 1 upon LC in the series resonant frequency, and omega P is given as square root of 1 by L into 1 by C plus 1 upon C prime is the parallel resonant frequency, expressed in a different way in this case. Since C prime is much greater than C, we have seen the values in the previous slides, it is much greater than C, then omega P is equals to omega S. Is it not? If C prime is much greater than C, then omega P equals to omega P is what? Parallel resonance frequency. Omega S is series resonance frequency. Yes or no? Now, omega, if this is much greater, then this term can be neglected, and hence you will get omega P equals to omega S or not? Yes, Pratham, Aman.
Yes, sir.
Yes.
For omega S less than omega P, the reactance is inductive as shown here, and outside this range it is capacitive as illustrated in this figure. The loop gain for the general oscillator. Actually, here we have shown a diagram here in this book, in your book. The basic configuration of many resonant circuit oscillators. I mean, this diagram is showing a general oscillator circuit. Keep taking a different value for Z1, Z2, etc. You can form different crystal, I mean a different oscillator. Okay, that's what we will see. So loop gain for the general oscillator circuit can be written as minus AB equals to plus AB into X1 by X2. This is X1, this is X2. If impedances are pure reactances, either inductive or capacitor, then Z1 equals to this X, Z1 equals to JX1 and Z2 equals to JX2. There is no resistance, only reactance part is there. And Z3 equals to JX3. We know for an inductor, known to you, and for capacitor it is minus 1 omega minus 1 upon omega C. Since minus A beta must be positive and at least unity in magnitude, then X1 and X2 must have the same sign, that is AB positive. In other words, they must be the same kind of reactance, either inductive or capacitive. Is it understood? Here, from the general configuration of the oscillator circuit, we try to obtain this one FET-based 1 MHz crystal oscillator. For that, which one is replacing what, that we are going to discuss. A variety of crystal oscillator circuit is possible from the general configuration. If in the basic configuration of figure 14-32, a crystal is used for Z1. For Z1 crystal, 1 MHz crystal is used. A tuned LC combination for Z2 is used. Tuned LC combination is used for Z2. Okay. And the capacitance CDG, this is CDG, capacitance between gate and drain terminal of a FET. We know that FET has lot many capacitances already into it. I mean, you can say intrinsic capacitance, not externally connected. So that the capacitance CDG between the drain and gate for Z3. Okay, the Z3 is replacing this one, Z3. This is equivalent to Z2, and this is Z1. Okay, then we get this configuration of FET crystal oscillator, which can operate at 1 MHz. For the loop gain to be greater than unity, we see the equation 14-69 that we have written earlier, that X1 cannot be too small. Hence, the circuit will oscillate at a frequency which lies between omega h and omega p, but close to the parallel resonance value WP. And since omega h is almost omega p, the oscillator frequency is essentially determined by the crystal, not by any other components of the circuit. Okay, this is what your crystal oscillator. So read it. It is a re-look of this topic because we have already studied in your previous courses, and these two topics, crystal oscillator and ONB oscillator, are there. That is all finished now. Now we'll start another topic, which is current mirrors. What is the principle of current mirrors? That we'll start with, and some current mirrors we'll see. That some of the current mirrors will be bijective version, bijective based, and few will be Mosfet based. Okay. What is the principle of current mirror? That is here. The current mirror uses the principle that if the VGS of two identical Mosfets are equal, their IDS should be equal. Means Mosfet, any two Mosfets, for example. Here Mosfet is here, and one Mosfet, another is here. Okay, it is drain, source, gate, drain, gate, and source. The current ID flowing through the MOSFET, ID or IDS, ID. Let's say, let me call ID1 and ID2. The ID1 may be written as if they all are both are in saturation, both in saturation region. So what is the equation for current of a MOSFET in saturation region? Can anybody say? Are you remembering? Beta by 2 into VGS minus VT whole square, where beta equals to mu n C ox W by L. Is it not? Yes or no?
Yes, sir.
So this is the equation. Now, if VGS, this voltage between these two terminals is same for VGS1 and equals to VGS2. VGS2 is same, and of course the devices are masked. It's a masked devices. Masked devices. For masked devices means VT is same for both, and so W by L same for both. Then will there be any difference in ID1 and ID2? Yes, beta equals to VGS2 minus VT. Will there be any difference if you have same WL for both the MOSFET, same VT for both the MOSFET? Say this is VT equals to 0.5 volt. Suppose this you have taken as W equals to 44 nanometer divided by 22 nanometer for both. See, is there any chance that it will be differing? ID will be same or not? ID1, ID2? No, wrong. Yes, boys. So, principal Aman, are you there?
Yes, sir.
So, if devices, both the MOSFETs are same in the sense, masked, VT same, W by L ratio same, and if VGS are same, current will not be same. ID1 will be ID2 or not?
Yes, sir. It will be same.
Same. So that is the principle used here. The current mirror uses the principle that if the VGS of two identical MOSFETs means masked MOSFETs are equal, their IDS should be equal. This is the principle used, and further we'll discuss in the next class. So leave the class and join other classes.